Okay, so this is the week 5, and we have our physics toolbox. Right? This is how I like for you guys to think about these equations. That they are tools. It's like a screwdriver or a hammer or something like that. It's that you need to use them with the pieces of information that you're given. So the pieces are like you're building something, right? And then you use the tools to come to an answer, to arrive at some built thing, some product. So in the toolbox, what do we have so far? We have, as you know from last week's review, the force equation. We have the electric field. We have the potential energy, the voltage, and we also have the flux. So I want to pay attention to the flux because we're going to use that equation to derive new equations. So, what are we adding? We're adding this one right here. This is called the capacitance. Today we're going to be talking about capacitance. This looks arbitrary, but I'm going to explain where it comes from. It comes from the electric flux, and we'll see. There's also another one, which is the potential energy of a capacitor. So C, capital C in this case, is talking about capacitance, the ability to store charge. How much charge is stored on this electrical component called a capacitor. And this is how much energy is stored. So it stores charge, and it also stores energy. And it's given by this equation. We're going to explain these two equations. We can see that capacitance is equal to epsilon naught, permittivity free space, which is more or less just a constant for our purposes in our class. And A is the area. We'll talk about what it is. And D is the distance between parallel plates. So let's actually put these in our toolbox, and let's talk about the first equation here, right? So where does this come from? I always love asking the question why. So it just doesn't come out of thin air. It comes out from something that we already know, and that is the electric flux. Okay? The case that we're talking about, this equation is applying to, so you write in your notebooks, this is for parallel plates. Okay? Parallel plates. Parallel plate capacitor looks something like this. So this is the image I want you guys to draw in your notebooks. It's going to be two rectangular plates, and they're connected to some battery. And then one of them is going to be, if this is the positive terminal, it's going to make this one positive. I'm going to avoid it, so it's going to make this one positive, I believe, and this one is negative. Yeah, is that correct? Should make that one, yeah. All right. Where does this come from? Well, it comes from finding out, first of all, what is the electric field between the plates. All right, what is electric field between plates? To find out the electric field between plates, let's just look at one plate. Let's just look at one plate. So, the plate, again, this is the area, right? This is the area, and then D is the distance between those plates. That's what this equation is talking about. Talking about parallel plates, capacitor. So you see, the first point is that it's dependent on the geometry. So if you have a different capacitor with a different geometry, it's going to be a different equation. But for our purposes, we're just going to look at this one, this most simplistic one. So we have that. Now, let's take one of the plates. Okay. One of the plates. And let's look at this drawing here. Let's find the electric flux. Because that electric flux, as we know, is E dot A, right? So let me write this in general. Electric flux equals E dot A. We just learned that. And if we look at the electric flux of one plate, right, we see that when we draw a Gaussian surface, we can draw it in a convenient way so that the area is parallel to the electric field, so that the cosine theta equals 1. The angle between those two vectors are 0, so cosine of 0 is 1. And therefore, this simplifies down to this. The area, there's two areas. See? There's two areas. So that's why the magnitude of that is going to be 2a. So this, and we know that the cosine of theta equals 1 because theta equals 0. Okay, so we have this. We're going to introduce this new symbol called the surface charge density. So we're familiar with linear charge density, right? Where we said that linear charge density is the total charge over the total length. Now we're just going to increase the dimension, and we're talking about this symbol sigma. Let me draw that better. Sigma equals the total charge per area. One more dimension. Now, you see that eventually we're going to talk about the charge density per volume when we go to 3D. But we're doing the surface, that's why it's just 2D. So, we're not doing linear density anymore. Linear charge density, we're doing surface charge density. Okay, so that's what this sigma is. So let's write this over here. Sigma equals total charge per area. Okay. Did you guys see the substitution? How they would make the substitution in algebra? And then we arrive at this, E. Because I can divide by 2a on both sides, right? Divide by 2a on both sides, make the substitution, and then you get sigma over 2 epsilon naught. Try it out in your paper. Take a second, write it down, try it out, see that that makes sense, guys. I'll wait for 30 seconds. Okay, got it? Got it? Okay, so let's go back, and so let's erase this. Okay, let's go back. We also have that, yes, it's equal to this, but it's also equal to Q over V. Right? So, we can say this. I'm going to go straight across. So we have C equals Q over V, which is also equal to Q over, let's remember this, what is V equal to in terms of electric field? So let me just refresh you guys' memories, right? Voltage. The units are going to be Newton meters per coulomb. Remember how I was saying that there's two ways to look at voltage? Newtons per coulomb, force per charge, that is electric field. Electric field times a distance, over a distance, electric field over a distance. So, what I'm trying to get at is that voltage is the electric field times the distance between the plates, D. See that? And, let's go further. Let's replace what E was in here. So we get this sigma and this here. Oh, remember this was one plate. This was one plate. We have two plates now. So let's just write that out. So we have sigma over 2 epsilon plus sigma over 2 epsilon. 1/2 plus 1/2, right? It's 1. So that's why it's just epsilon for 2 plates. This is for 1. Plate inside that thing. So we have 2. So since we have 2, we're talking about 2 of them. We're going to plug in for E. So E is sigma over epsilon naught. Sigma over epsilon naught. Flip it, right? I flip it. And final cancellation, we get, voila. That's where the equation came from. It came from finding the electric field between the parallel plates using the flux equation. Then from that, we use surface charge density. And then we also manipulated that voltage equation. We know that voltage is going to be some electric field times the distance. That's the logic. That's where that equation came from. Make sense? Okay. So, alright, and now, let's erase this. So you guys have that now? Awesome. Next thing is just the little things. Here's a little thing that you can use, a little pyramid, right? It's just a silly little thing. It's just saying like, okay, if you manipulate the equation, because you're going to do this for the circuits, C times V, right? Multiplied by V on both sides. CV equals Q, right? So if you like kind of cover it up, right? CV is Q, right? Q over V, what's remaining? The C, right? And then Q over C is V. It's a little silly thing. Just so you guys, so you don't have to clutter your equation sheet when you're taking your test. You can just use this. Just a little triangle with the 3 letters. Okay, now, I think you guys already know this one, right? When capacitors are linked together in a circuit in parallel, like this, how do we find the equivalent capacitance? Yes?
You just add them?
Yeah, you just add them. It's the opposite of resistors. See, you just add them, so it's going to be C1 plus C2 plus ... however many that are in parallel. Okay, and then in series, we do this other peculiar thing, right? What do we do? When we're in the line, what do we do? We're going to do, I'm going to write C1 plus, oops, messed up. 1 over C1 plus 1 over C2, but that quantity, 1 over that. I always forget that. So don't make that mistake. It's 1 over that equals of that quantity, 1 over. And that equals the equivalent capacitance. That's basically it. We're talking about capacitance. That's all we really need to know about this new capacitance equation. So, with that said, let us now turn to the potential energy, the energy stored on the capacitor. So energy stored on the capacitor, why? Right? Where does that come from? Well, we know, remember in our diagram, I had force, electric field, potential, and voltage. How did I go from each side? What did we do? How did I go from left to right? Anyone remember this from last week? Yes?
You remove the Q?
Yeah, you
divide by Q.
Yeah, left to right, you would have to divide by Q, right? From right to left, you have to times by Q. Yes, that's why it's times by Q. So Q times voltage is going to give you potential energy. So now this is true for the total, and you know how I always talk about how it's going to be in proportion to du, infinitesimal potential energy, equals an infinitesimal charge times voltage. Cool? So now we're going to use this. We're also going to integrate both sides to find what this is going to be. We're going to integrate this. When we integrate this, we can plug in V. So the integral of this is going to be U equals integral Q over C dq, right? C is a capacitance, that's a constant. I can factor that out. 1 over C integral Q dq. We're integrating from, you could say, 0 to, let's just say we're integrating from 0 to Q, right? 0 to Q, all the charge from all the charge. And we're going to say this is going to be 1 over C, oops, 1 half Q squared. Integrate from 0 to Q, right? And so then that's going to be, so do this along with me, right? do this along with me. So you have Q squared over 2C, right? Cool? So cool? All right, now, we're not quite there. This is CV squared. We have Q squared over 2C. Well, that's the same thing if we rearrange it with the equation. So we have Q squared 1/2 over 2C. So C, right, equals Q over V. I want to find Q, so it's going to be CV equals, Q. I'm just going to use capital, lowercase, doesn't really matter. So if I were to take this Q, square it, C squared V squared equals Q squared. Boom. U equals 1/2 C squared V squared over C. Lovely, right? And I love using red one. Cancel, cancel. And then we get U equals 1/2 CV squared. Boom. That's how we get it. So it's not arbitrary. It comes from somewhere. It comes from the concepts that we know. I want to embed that idea in you guys that when you're learning physics or when you're learning anything technical, these equations that you pull out of the book or the appendix, they come from somewhere, and you can always rederive them, and they make sense. It's good to understand where they come from so that we can better use them rather than just looking it up. We don't know what each of those variables mean, and we might use the equation the wrong way if we don't understand its origins. All right? Cool. So that's where those two equations come from. All right. So, with that said, let's take a break. All right, so with this problem, we have a circuit as shown, and we have the capacitances of those pieces, right? I went ahead and just said that it's 1 farad and 5 farads. On the sheet, I don't know why they printed the letter C. It makes it awfully confusing because C is like, is it coulombs? No. Is it capacitance? No. It's farads, right? Capacitors have farads, so just make it F. Right, so it should be 3F, 1F, and 5F. All right, and the first step about solving circuit kind of questions is to break it down so we can clearly see what's in parallel and what's in series. And that's what I've done here. So you see that this drawing is the same as this drawing. Let's look at the critical points, A, B, and C. Right, A is that first point, right? That's the same thing. C1, that's fine. B is where it splits. So this splits like this, but we can say that B splits. So then I can draw these two parallel lines. And now I know that C2 and C3 are in parallel. Okay? So this chunk is this piece here. And we're going to solve that first problem here. It's asking, what is the equivalence capacitance of this whole set? So let's break that down even further by looking at the parallel capacitors 2 and 3. So take a look at this. Points B and C here, right? B and C. These are in parallel. This is the same as replacing this with this. That's the idea of equivalence capacitance. Do it in pieces. So I use this notation. I'm going to say that the capacitance of 2 parallel with 3 is, and when it's in parallel, what do? We add. So we're going to do C2 plus C3. 2 plus 3, that's going to be 6. So right up here, C2 parallel with 3 is 6 farads. So imagine I take this, erase it, and put this piece in here. Let's actually, not imagine, let's actually just do it. Right, so let's do it. Let's replace this with that. And we have point B and point C. And we have, boom, the equivalent capacitance, and that's going to be called C2 parallel with 3, which equals 6 farads. And this one was 3 farads. Right? So that's what we've done. We've just replaced it, and it's the same circuit, just a little more simplified. Now, we see that this situation is that these two are in series. So now we must use the series equation one. So C equivalent is 1 over 3 farads plus 1 over 6 farads to negative 1. Common denominator, multiplied by 2 over 2. That's going to be 2 over 6 plus 1 over 6, 3 over 6. 3 over 6 is 1/2. Inverse of that, 2. So you get 2 farads. So the equivalent capacitance is 2 farads. So this is saying, if I were to replace these two capacitors that are in series with one giant one, that one giant one would have a capacitance of 2. Okay? So that answers the first part. What is the equivalent capacitance of capacitors? CEQ equals 2 farads. Okay, got that. State the ranking of the capacitors according to the charges they store from largest to smallest. Okay, here we go. To answer this question, what I had done was to look at it concretely by purposely picking a number for the voltage so that I can just look at the numerical values to determine what's larger and what's not. So I picked a convenient number, and I'm just going to do, for example, you can do this with any number, but I'm just going to pick that the voltage here was 9 volts. I'm just going to say it's a 9-volt battery. Okay, so let's say I put that number. Then we can see with the numbers how it works out. Okay, so let us do this. Let's erase this. So we have that piece, that's important. First off, let us do C equivalent times the voltage. That would equal the total charge. Right? So if I'm looking at it as one giant thing, it would be CV equals Q, the total charge of that whole thing. And that would be, well, C equivalent was 2 times the voltage, which is, I said, was 9. 18 coulombs. 18 coulombs. Okay, so that's not capacitance, that's coulomb. Let me just emphasize that. So it's going to be coulombs. Okay, now from there, we have to find the voltage. So let me just redraw that again. That was C1, and that was C2 parallel 3. Going back to this picture, we can see that the voltage across that, I'm using another marker, the voltage across this, call out V1. Let's call this the voltage across this, V2 and 3, okay? So that's going to be voltage across 18 over the capacitor, which is going to be 3. 18 coulombs over 3 farads, which is 6 volts. So the voltage across V1 is 6 volts. And we get a nice number there. Because V equals Q over C. Okay, so that's the first one. Let's look at the voltage of this, the other part here. Voltage 2 and 3. Well, it's going to be 18 coulombs charge over that equivalent capacitance, which we said was 6. So that's going to be 6 F. So 18 divided by 6 is 3 volts. Okay, that's for the combined. So we see that we kind of already answered part C. in advance because we're kind of seeing that voltage 1 is larger than voltage 2 and 3, but voltage 2 and 3 are the same. So that's that, kind of like alluding to that. Okay, having that, we can now do this, which I want to draw really good. C1V1 equals Q1, which was 3 farads times the voltage, which was 6, equals 18. The coulombs. Okay, that makes sense. That's not a surprise. Now, let's do the next one. C2V, V2 equals Q2, because I want to figure out how much charge is on the second one. So that's going to be 1 farad times a voltage of 3 volts. So 3 volts equals 3 coulombs of charge. Okay? And lastly, C3V3 equals Q3. C3 was 5 farads times 3 volts, which is going to be 15. Look at that. So let's rank them in terms of which capacitor stores most charge, the most to least. Well, we see that it's going to be Q1 greater than Q3 greater than Q2. See that? So with the numbers, by plugging that in, you can clearly see that those numbers are bigger in that order. That's like a typical question of how to determine that. So it was really difficult for me last night trying to figure it out without numbers. Maybe you guys can think of a better way to do it without having to plug in the actual number. But I like this way because it just shows it very nicely. Notice this. I want you guys to notice this. Remember how I was saying that the voltage, the charge that fills them up, it's going to be the same amount of charge on the first capacitor and the same amount of charge on this combined system, 1818. Notice that the voltages add 6 volts plus 3 volts, adds to 9 volts. That's good because when things are in series, the voltages add to 9. And look at the charges. This was 3 charges at 3 coulombs, and this is 15 coulombs. Yes, the combined amount of charge on that combined system was 18. So that makes sense. There's a way of checking yourself. That makes sense. So this is 18 amount of charge. That was 18 amount of charge. The voltages add up to the number that we said was 9. That's how you break this up, this kind of question. And the answer is A, B, C. And lastly, let's go for the home run. Let's answer D, right? Let's answer D. Whew. So actually, let's take a break there. For this last part, D, it's a real good conceptual question, and this is how I would go about solving it. This would be a very typical problem on an exam. Everything, you've just done all the work, and then all of a sudden they hit you with something has increased. How does the overall system change? In this case, we're looking at, explain what happens to the charge stored by each capacitor if C3 is increased. So let's just take from the audience, give me a number that is larger than 5 farads. So like, someone said 7? 7, okay, so 7, the new number is 7. 7 farads. That means that the overall equivalent capacitance will also change. So we have to recalculate what this is. I remember we're going to do this. So this is 7. 7, so let's say this C prime is 7. And C2 was still 1. They're in parallel, so I add them together. So I add them together, that's 8, right? And then this is in series with the C1. So let me just write it here, write some space, so CEQ equals 1 over 3 plus 1 over 8 to negative 1. When you get common denominators, because this is 8 and this was in series, so it's 1 over 3, 1 over 8, so that's going to be times by 8 is 24. No, this is 8. This is 1, yeah, so this is 8, and this is 24 times by 3 over 3. This is 24, this is 3. So that's 11 over 24. But I have to reverse that. So C equivalent is 24 over 11. Okay, got that? So it's going to be 24 over 11. Doesn't give us a nice number, does it? Oh, luckily I have it calculated here. It's going to approximately equal 24 over 11. No, 24 over 11 is
2.18.
Thank you. So this is 2.18, approximately. So 2.18 times 9, what does that give us?
19.63.
Thank you. So 19.63 coulombs. Okay. So now we have that. We know that the charge that's stored on this capacitor and the charge that's stored on this combined capacitor will be 19.63. So if I take 19.63 coulombs divided by the charge of capacitor 1, which is 3. So what's that number? 9 divided by 3 farads. Help me out there. What's that voltage going to be? This divided by this.
6.54.
6.54. Thank you. Volts. And then what's this one? This is going to be the same amount of charge divided by the capacitance of this combined system. That combined system was 8. Right? So this divided by 8 farads. What's that number going to be?
2.45.
2.45. Awesome. 2.45 volts. Okay. Now, we're going to take these numbers. We're going to plug them in here. So, this one, its capacitance was 3 farads times the voltage, this new voltage across that capacitor, 6.54. What's that number going to be?
19.62.
19.62. Next one, capacitance of 2 was 1. 1 farad times the voltage, 2.45. That's easy. That's 2.45. And then lastly, C3. C3 was, oops, get rid of that. C3 was 7, right? So 7 times, and what does that give me? 7 times 2.45?
17.15.
17.15 volts. Okay, let's highlight this. So our new Q1 is this. Q2 is this. Q3 is this. What happened? Well, Q1 increased. See that? Q1 increased. Q2 decreased. Q3 increased. See? So that answers the question. If C3, if I change that one capacitor right here, if I change that just by a little bit, what happens to the charge stored by each capacitor? This is what happens. For this particular case, where I chose voltage was 9. Now, you could do that without a specific number. You would just get an expression that would be larger, is what would happen. But I think I like this concrete approach. Even though it's very meticulous, it shows clearly that what happens to the charge on each capacitor. Okay? Awesome. So we have a parallel plate capacitor with an air gap in between that's separated by a distance. So when I look at this, I go ahead and underline that. That's my D. And a plate area, look at this, they tell me the area. That's my A. The plates are charged to a potential difference of 250. This is your voltage. and disconnect it from the source. So it was charged up, and the thing about capacitors is that when you connect it to the battery and it's charged all the way up, the voltage on the battery is going to be the same voltage that's going to exist between the capacitor. That's what happens. So if we charge it all the way up, then the capacitor potential difference also 250 when it's charged all the way up. So, and then we're going to disconnect it, but it's still charged because those charges can't jump over that air gap unless there's some wire that allows them to go between or something like that. There exists some potential difference between them, and so then the capacitor is then immersed in distilled water. Okay. Assume the liquid is an insulator. Okay. Determine these three things: the charge on the plates before and after immersion. So, immersing this capacitor in distilled water is like putting a material in between the plates. Because before there's just an air gap. And when there is an air gap, the K is approximately 1. That's why you don't see it there in the equation. But normally, for most materials, K is larger than 1. So this mixture material inserts itself, and it basically prevents the electric field lines from going through it. You can kind of think of it like that. And so it would, I believe it would, let's see here, I believe it would change the voltage. Yes, it would change the voltage between the capacitors because that dielectric is in between. Alright, so let's look at this now. We're going to use our equation here. C equals K epsilon times area. You know that. Just keep this one. The charge before and after immersion. So, let's do this. Charge equals CV, right? And let's make that initial. Initial. That's going to just equal epsilon naught A over D, that's my C, initial, and V, which was 250. Right? And if you plug all those things in, epsilon naught 8.85, again to remind you guys, times 10 to the minus 12 Coulomb squared per Newton meter squared. We know area, we know distance, voltage, we can calculate this. What does that end up being? Ends up being, write this down for you guys, 369 picocoulombs. Pico, you guys remember what pico means? P, is the subscript. I believe that is 10 to the 12th, minus 12. 10 to the minus 12, I think. I'm wrong. Right. I remember that nano, right? N is 10 to the minus 9, and I think pico is 10 to the minus 12. That's the unit of picocoulombs. Okay. All right. So that's before immersion, and let's see here. Immersion's the value. Oh, the answer sheet says that the charge before immersing it in water and after water is the same. It's the same value. Wow, that's interesting. The charge on the plates. Actually, that kind of makes sense because the water doesn't prevent the charges from building up on the plates. But let's look at another quantity, which is the capacitance. Does the capacitance change by doing that? Let's see. So this is going to be true before and after immersing it in the distilled water. All right. Part B, the capacitance potential. So let's look at the potential. The capacitance. So let's use the subscript F for final after we've merged it. That's going to be K epsilon naught of the K, right? Over D equals Q over V. F, right? With voltage afterwards. And let's see here. If we look at distilled water, if we look it up in the in the table of charts, every material has its own dielectric constant. I think, and then this is telling me that the dielectric constant for distilled water, I believe, is 80. Okay. And so if you look at the capacitance, we know E, we know A, we know D, we know K. We looked it up in online or on the table, and you're going to get 1.2 times 10 to the minus 10 farads. And this is where I want to introduce the units of capacitance is farads, because it's in honor of Michael Faraday, who contributed a lot to electromagnetism. So we use the F, farad, to denote capacitance, the units of capacitance. And to now solve for VF, we could do Q over C. F. Right, just flip the equation around. And so that's going to be C initial. It's also the voltage is going to be, the voltage initial over final. And let's take a look at this. Does the charge, see, the charge remained the same before and after immersion, so I'm going to use the values that I know. And then after immersion, so I'm going to see what this is what's going to give us. And therefore we get, this is going to be epsilon naught A over D over this one is K epsilon naught A over D. Oh, no, sorry, wrong symbol. Just use E. And cancel, cancel. And then you're going to get VI over K, which, let's just plug it in. The initial voltage was 25 volts over K of 80. That's going to give us 3.10 volts. So that's going to be the volts there. And the capacitance, so we calculated the capacitance? Yes, we did. So we found the capacitance and potential before and after immersion. So this is after immersion, is this, and then that's the voltage after immersion. Yes. Okay? And lastly, the change in energy. So if there's change in energy, we're talking about the potential energy stored in the capacitor. So, we're going to use the other equation, right? The U equation. So, before, we use U initial equals 1/2 C initial V initial squared, which is, we can set equal to epsilon naught A over D, that's my capacitance, and then over 2, right, it's over 2, and 3 initial squared. Yes, initial. Final, what's the final one? Write it. It's going to be 1/2 C final. B final. We calculated these from before, part B. You can look back in the video. And just write that out. It's going to be 1/2 K with the K one, because C minus the K is it's immersed in water, over D times V initial over K. Oop, squared. And get some cancellation going on. Well, this will be K squared. I have to cancel out with one of those, right? Actually, I probably won't write that up, but you can see here that you're going to get epsilon naught A V initial squared over over 2, let's write d, let's write k. That's not the differential, right? That's not differential, that's d times k, distance. It's not dk, the integration thing, no. Just want to make that clear, that's d times k. And we want to find the change in energy. So I need to do UF minus U initial. So I take this piece minus this piece. And when you do that, you take this piece minus this piece. U final minus U initial. We want to get the common denominator, multiply by k over k. What you end up with is epsilon A V initial squared, factoring it out, 2dk. Wonderful, that's the answer. So if you go ahead and do that algebra, because I want you guys to practice that, go ahead and do that. Take that minus that. Factor out the pieces that are common to both terms. You get that. That answers all three of the questions. Any questions on that? So now that you guys understand dielectric constant, take a look at worksheet problem number 1. Now it talks about dielectric. You might have to do the opposite kind of solving. All right, here we go. We have a situation where one of the capacitors is already charged a little bit. So it has 15 volts. This one is not charged. Then you want to connect it by flipping that switch over. So then it's not the case where the capacitors are uncharged. Like one of them was already charged. And so now what's going to happen, find the new potential difference across both capacitors after the switch is closed. First thing is to take a zoom out to look at the overall. So let's find the overall charge, the initial charge. So Q equals C V. Let's look at the charge on there. So the charge on here is going to be 10 microfarads times the voltage difference, 15, equals 150 microcoulombs. That's the amount of charge on this guy, starting out. And then additional charge is pushed through this. It's going to push through once you flip it over. It's connected. And giving the smaller capacitor a charge Q. So imagine the charges are building up. It's building up. So it's building up, and it gives a little Q on there. And then this one pushes over here, and that gives a little Q over here, right? One little charge. So it gives a Q, and then that one pushes it and gives another Q over there. So if I were to look at, let's call this the smaller one. Capacitor, let's call this a larger one. We know that 50 volts equals Q. So when it starts, it's going to have one little Q on the 5 microfarad capacitor, smaller one, plus 50 microcoulombs. See, it started out with 150 plus Q. That's the little subtlety. You see, that's how to make up for that. Because otherwise, it was not charged. It would be also Q over that. But it started out with already some charge, because it was already charged up to a potential difference of 15 volts to begin with. And that one's over the 10 microfarads. Okay, so if find the potential difference, so we want to find Q. We want to find the Q here. We want to solve for Q. We have everything else. We want to solve for Q. When all said and done, you do the algebra. You're going to get 500 microcoulombs equals 2Q plus 50 microcoulombs plus Q. We have this. This step to this step, I skipped some steps, but what essentially am I doing, right? I'm getting a common denominator, I'm adding them together. That's all I'm doing. And get to this step. Now we can combine the like terms, 2Q, Q, that's 3Q. Subtract over, so what do we get? Q equals 117 microcoulombs. And so where is it now? Okay, so let's get some room. So for the smaller one, we're going to have V equals Q over C, the capacitor, the smaller one, which is going to be 117 microcoulombs over 5 microfarads. The micros cancel, we get 23.3 volts. That's going to be the voltage across the smaller one. And then, for the larger one, voltage equals 150 microcoulombs plus 117 microcoulombs. Add them over 10. It's going to end up equaling 26.7 volts. Voila! So it's the little subtlety of plussing the Q added on to the initial amount of charge it had. So it makes it slightly a little more complicated. But that's how you go about solving this kind of a problem. Cool? Alright, we're good on time. Yes?